6 years ago, I designed my first Nixie clock using our Nixie tubes. It was a single tube clock called Solitube. It was shipped to customers as a kit and they would assemble it themselves. It was quite successful. We shipped around 30 clocks in a short period of time. And soon after customers built it, they were sending us questions whether we could add some new features for the clock. So like a night mode, so that the clock would turn off the tube during the night and similar things. And the clock was based on Arduino, so it was possible for me to update the software and send the customers the code, and they would upload the code to the clock, but it was quite difficult to handle this update. So next year, in 2015, we were designing a new clock with a friend of mine, Daniil. His part was the design, the metal case, and all like the manufacturing of the case, and my part was to make the Nixie tubes with the electronics. And I still remember this thing with the Arduino based clock, so this time I wanted to have the possibility of easy upgrade of the clock. So I looked around and I found nice IoT module called Photon. This Photon helps you to keep your product wirelessly connected to internet and do all the firmware upgrades and also other functions remotely. So it's a very nice thing. I used it for the Sturnus clock and I built the electronics around this Photon module. In the end, we made just one clock and sold it to customer in Mexico. And then we found that the manufacture of the stainless case is very difficult to make, and we put this project on hold. But we want to make the whole series what we planned, 20 clocks, one day when we find how to actually make it, but that will be later. Fast forward year 2020. We have several hundred clocks shipped to the customers, mostly Zen clocks and Pierre clocks. And I have new firmware for them containing new features, some bug fixes. And in today's video, I want to show you how it looks when we update the firmware. We have roughly 600 clocks all around the world. They are all connected to our cloud. When we want to flash the new firmware, we need to send the firmware binary file to the cloud, and the cloud will take care of delivery of the firmware to all the clocks. The clocks which are online will get the new firmware immediately, and the clocks which are offline will get it once they get connected to the internet, to the cloud. This is quite serious thing. We don't want to break anything up, so first, before flashing this firmware to the cloud, I want to make sure that all the bugs which were reported by customers are fixed and that all the new features are working well without breaking the existing functionality in the clock. So I prepared two new clocks, one Pierre clock, one Zen clock. They are running the most recent firmware what is on all the clocks of all our customers. And I'm now going to flash the new firmware into them. The firmware consists of two parts. Like one is the actual user code of the clock, and another one is a system firmware. It's something like operational system. And there is a new operational system released by Particle. This is the company that produced the Photon module. Before we can start using the new firmware, we need to flash this operational system first. This is all done by the cloud automatically, but we need to make sure that all this procedure will actually work well. Great, so I can flash the firmware into the clock. So this magenta color means that the firmware is just being updated. So the first part is flashed in the clock. Okay, so the clock starts. It looks like the clock is updated. get the revision of the clock. So this should be number 19. Yes, perfect, number 19. And now the system firmware version. So it's this number. So I will insert the number here and convert it to hexadecimal format, and it's 1.5.0, which is the most recent system firmware of the particle. So perfect, that works well. Okay, so the clocks are now running the newest firmware and I want to test it. I have a shell script which will call the individual functions and it will use me as a feedback. I will just confirm whether the clock displays what it should display. I worked on the previous firmware versions alone, so it was possible for me to keep track of all the modifications and changes in the code. But this new version involves some new code from Sebastian and lots of code from Lukáš. We hired Lukáš last year to make the iOS application for our customers for easier configuration of their clocks, and he liked that connection of hardware and software and later volunteered to add new features to our clocks. To name one, Lukáš implemented Apple HomeKit so customers can automate behavior of the clocks. This was a huge amount of work and lots of new code. With more people working on the code, it becomes more difficult to keep the code without bugs, so I'm now trying to find a way how to test all the clock's functions after we make changes in the code. If you are into software a bit, you know a technique called unit testing. The idea of unit testing is to split a complex code into small units and test each of these units separately. Let's say you need to do a multiplication in the code, so you would write a unit test routine which would send numbers to be multiplied into your multiplication function. The function would do the actual computing like a black box, and the unit test would check the result. Now when you make changes in the multiplication function and accidentally leave a bug in it, the unit test routine will catch the bug because the result of the multiplication will be incorrect. Okay, what you are watching now, I made a simple shell script which sends commands to the clock and suggests me what output I should see on the clock. So, for example, here we have a function which takes care of automatic switching between summertime and wintertime. So the script is sending future timestamps to the clock and the clock calculates the time to be displayed. I compare the time on the clock with the time that the script expects, and if they match, I know that this function works properly. As I mentioned, the clocks are connected to the cloud and all the communication between the cloud and the clock is encrypted. For this encryption there have to be some keys. On the clock the keys are stored in a flash memory. And it can happen that the flash memory gets corrupted, and in this case the clock is not able to connect to the cloud. So for this case we have to have a way how to restore the keys remotely in the clock without replacing any hardware. Just for information, among these 600 clocks we already had 3 cases like this, that the keys were corrupted and we had to replace the board with the electronics to the customer. So this LED light comes from the photon, and the normal behavior is it will start blinking green, then aqua, and then it goes off. When it goes off, it means that it's fully connected to the cloud. So this is the normal behavior, and now I'm going to upload the corrupted file. So, okay, fast forward, I downloaded keys, I corrupted the files, and now I'm going to post a bad server key, right? The clock replied okay. And let's see the light. It will go green, cyan, and now it should red flash. Now it should make some red flashes. Yes, perfect. Okay, by these red flashes the clock tells us that it can't connect to the cloud, that there is some problem. I can see here errors. Handshake data decryption failed. Perfect, this works. We managed to corrupt the encryption keys for the server. And now I'm going to upload back the correct file and we will see whether the clock can restore the communication with the cloud. Okay, so the clock now has the correct server key. So let's restart it. Green, aqua. Yes, it went off. So now at this point the clock is fully connected and let's check the connection once more. True, yeah, it's connected. So this feature works. We know that we are able to restore corrupted server key without plugging any cables or replacing anything in the hardware. I see that there are several devices which are already being updated, like 1, 2, 3, 4, 5 Pierre clocks. Yeah, there are more and more, but still 0 fully updated devices. We can see it here. So, at this point, it all started going wrong. Okay, I see some errors like file too large, flash fail. That's not good. One of the things I wanted to show off in this video was the smooth and elegant remote update process we can do on our clocks. I already did this 17 times before on our production clocks and many times more during the programming, and guess when it breaks, when you finally show it publicly. Ah yes, first device is fully updated. Okay, so maybe... Ooh, what does this mean? File too large. Never seen this. We can make up to 128 kilobytes of binary and the Pierre has 119, so we are still safe. In the end, I decided to switch back to previous firmware and get better understanding of that problem first before trying to update the customer's clocks again. Okay, it seems that the problem is not getting solved by just trying to repeatedly update the clocks, so I will revert back. I will take back the update to version 18 and we will see. So all the devices are now turning back to version 18. Okay, it seems that all the new clocks or all the clocks that were updated to the new firmware went successfully back to previous firmware. Yeah, device count 0. So that's great because we still have the connection to the clocks. There was no problem keeping the connection. We just had to take back the update. And I think I will now prepare several clocks here and I will try to reproduce this problem, because some clocks were updated, some not, and I need to find out why. In the end, the bug was pretty simple. There was a hard-coded maximal binary size of 108 kilobytes, so we couldn't send the bigger 119 kilobytes of binary into the clocks. To solve this issue, I had to contact Kalberer, who is developer of the cloud server that we use. Particle, manufacturer of the photon modules, runs the official cloud server with all support and continuous development. So maybe you are asking why we go the struggle of managing our own server. The main reason for it is to not be dependent on third-party infrastructure. If something happens with Particle, for instance, they can be acquired by other company which can later decide to abandon the Photon platform, our clocks would be unusable and we would lose connection to them. Now in 2020 the Particle is established business, but in 2015 when I was deciding about the cloud, it was still a young startup short after Kickstarter, so the risk was quite high. Now back to our cloud. John developed the cloud server for his own project called Brewski. Brewski is a device which you connect to a beer keg, and it adds kind of user control to it. It keeps track of who pours the beer and displays it on a mobile application. So I asked John for help and he fixed the issue in just few days, which was great help for me. Thank you very much for this. Now with the bug fixed, I set up a small fleet of photons and tested the whole update process on them. And this time all went perfectly smooth. All clocks finally received the new firmware. Now all the problems are fixed and all the clocks are updated. There are some things which I want to clarify at the end. First of them, when looking back at the video, I'm afraid that I pictured the Photon platform a little bit in a negative way, which is not what I actually think about the Photon. The only problems we ever had in production, like in the customer's clock with the Photon, were with loss of the encryption keys which secures the communication between the clocks and the cloud. This happened 3 or 4 times, and if you use the official Particle cloud with the Photon, then the Photon can automatically recover the encryption keys in case it loses them. So it's our own fight to use the unofficial cloud. If you use the official cloud, this would never happen to you, so it would run really smoothly. That's one thing. Another one is why we use the cloud connection at all, why we just don't polish the firmware and deliver the clocks with the finished firmware to customers and just forget about any cloud connection. And there is one thing, it's very easy to synchronize time from internet. This is one thing. And another thing which is most important, which is the main reason why I decided for the cloud connection, is that there are still some information we don't have regarding behavior of the Nixie tubes, like the physical processes inside. Let's name one. It's cathode poisoning. Cathode poisoning is when you have these dark areas on some parts of the digits. It usually develops on unused digits because these unused digits are contaminated by the sputtered metal from the other digits. I'm planning to make a separate video on this topic because it's a very interesting topic. But now just really briefly, if you want to avoid the cathode poisoning from happening, you need to run a prevention cycle on all the unused digits, so you need to run them regularly. And the problem is that nobody actually knows how often do you need to run this cycle and for how long. So once I have answers for these questions, I can implement it into the firmware, I can tune the parameters, and then our clocks will have the maximum lifespan. If you run it too often, which is what we do now, then the customer needs to see the cathode poisoning prevention cycle too often. It's not dangerous for the clock, it doesn't limit its lifespan or whatever, but it might be annoying for some customers. So I want to tune it exactly to the values where you know that you are reaching the maximum lifespan of the tubes, but you are not seeing it too often if you don't want. To get these answers, we need to run tests. I actually set up here behind me several clocks with different parameters. Some of the clocks have like 0% prevention cycle, it's not run at all. So at these clocks we are observing how it looks when you run the clock without any poisoning prevention cycle, and the rest of the clocks have different values set up for the prevention cycle. So once I have the output from this test, I will be able to determine the exact values what we need to use in our firmware. And what I want to say with the cloud connection, if you have the option for updating the clock remotely, you can run these tests and update the clocks after years once you have the results. So this was the main reason, because if I decided for too low, let's say too low values for the cathode poisoning prevention cycle, the clocks we would send to customers would be limited in lifespan, like they would show the cathode poisoning prevention in short time span. So this was too risky, so I wanted to keep the way how to update the clocks even after some years when we will have the numbers from the research.